Hello, this is part 3 of the lecture on quantitative analysis methods. Z-scores then can tell us something about individuals and how they relate to populations, but only as long as those populations are normal. It's no good if we have non-normal populations. Unfortunately, that means most of the things we're interested in developments. Very many things are just not normally distributed, like income, land, livestock, any asset you like to think of. Most desirable things are non-normally distributed. They usually have skewed distributions, often positively skewed. So that's a limitation of Z-scores. But Z-scores are about individuals. We normally sample more than one individual. Normally. What effect does it have when we go and sample 10, 20, 100, 1,000 people instead of sampling one? What effect does that have? Well, as one of the learning activities in this session, you can look at this online sampling distribution demonstration, in which you have a parent distribution and you take samples. And here we have samples of size 5, and here samples of size 25. What it does is it takes a sample of size 5 from here and plots the mean, takes a sample of size 25 from here and plots the mean. So each square here represents an individual in the population. Each square here represents, this is the mean of one sample. So I've taken 5, averaged it out, and I've got this number. 5, averaged it out, and got this number. Here's a sample of 25. So this is 25, averaged it out, and get this number. And the idea is you can see that the sample of 5, when you have a sample of 5, the average of that sample varies less than the whole population tends to vary. Because in a sample of 5, the likelihood is that if you get a big one, you'll probably get some smaller ones and they'll cancel out. So you end up close to the mean. 25, that effect becomes even more pronounced. You tend to end up even closer to the mean. Anyway, these are the results that you'll see online when we do that activity. The nice thing about this is that the sampling distribution, this is called the sampling distribution of the mean. These are the individual values. This is what it looks like if you sample them 5 at a time and plot the means. This is called the sampling distribution of the mean for sample size 5. This is sampling distribution of the mean for sample size 25. It's got a much smaller spread. So if I pick one individual, I might get someone down here quite easily. I might get someone up here, well away from the mean. If I pick 5 individuals and get the average of those 5 is likely to be reasonably near, somewhere in this range. So I'm not very likely to end up here somewhere. If I choose 25, I'm very likely to end up really close to the real mean. Very unlikely to get, I have to get 20 odd big ones to get right up to here, and very few small ones. So it'd be incredibly unlikely that I could end up here if I have a sample of 25. So the spread reduces more and more for bigger and bigger samples. Now, this is all very well, of course, because this seems to work as long as we have a normal distribution to start with. But as we noted, most things do not have normal distributions to start with. Most variables have a very skewed distribution, or even a very messy, horrible distribution like that. So it's messy, untidy, and skewed. The nice thing is, though, once you take a sample of 5, if you take thousands and thousands of, you see that the distribution of samples of 5 still slightly positively skewed, but much more normal looking. Still a smaller spread. Samples of 25 starting to look almost normal. Very small spread. The mean of this is close to the actual mean of the original population. So even though the original population is very messy, if you take a big enough sample, it becomes symmetrical and indeed closer and closer to normal. And this is very handy. We can prove with advanced maths, which we're not going to do, unless you're really excited about doing that as your sample size grows larger and larger, for any distribution at all of the population, the sampling distribution of your mean has this standard deviation, which is the original standard deviation divided by the square root of n. So as n, the sample size gets bigger and bigger, this gets smaller and smaller. That's the effect of these things being narrower than the original, narrower. The other part of it is that the shape gets closer and closer to normal. Even if you start with something horrendous like this, the bigger your sample size gets, the closer it gets to normal distribution. That's called the central limit theorem, and almost all the tests that you're likely to meet rely on this to some degree. Final problem is with using this, and this is the last technical thing we're going to do really before we start to talk conceptually about what you can do with the tests, is if you were in a rural area and say you didn't know the mean rice yield, how on earth would you know the standard deviation of the rice yields? It's been bizarre. If you don't know the mean, you wouldn't know the standard deviation. So in these formulas that I've been giving you, you don't know that, so it's hopeless. So the solution is that you have to estimate what the standard deviation of the yields is by looking at how spread out your sample is. If you have a sample which is really spread out, the chances are the population is really spread out, and vice versa. If your sample is clustered tightly together, chances are the standard deviation of the sample is quite small. So instead of using this standard deviation of the population, which is impossible to get at, you work out the spread of your sample by working out the standard deviation of your sample. So you estimate the population standard deviation by looking at the sample standard deviation. And it's worked out in almost exactly the same way as I showed you before. I ought to mention that there is a slight difference, just for those that like to follow those technicalities, which I can show you here. This is the very tiny demonstration I showed you of how to get the standard deviation of these numbers. Now this is actually the population standard deviation, because all we're interested in here, we're just assuming that these are just all the numbers there are. We want to know what's the standard deviation. If we're now going to treat this as a sample that comes from a bigger population, we want to use this to estimate the spread in the population. We do almost exactly the same thing, work out the spread from this central mean 5. Except here, conceptually, this now would not be, instead of mu, we'd write that, because we're assuming that the mean of these numbers is just the mean of our sample. It's no longer the population mean. We don't know what the population mean is. This is the mean of our sample, is 5. Everything else will be the same working out. You get out to 34, but the different stage is that instead of dividing by 5, the number there are, you divide by 4. 1 less than the number of values. Because these things here, the variance here is actually the sample variance. This is the population variance. When you treat those numbers as though they're the whole population, and this is the population standard deviation. If you divide by 4, which is what this formula is telling you, to divide by n minus 1, then 34 divided by 4 is 8.5. Which is the sample variance. Sample variance is written as s squared, that's 8.5. And sample standard deviation the rest of the working out is the same, you see. So the only difference is this, divide by 4 instead of divide by 5. Then square root the answer you get. Oops. .92. So instead of getting an estimate, instead of finding a standard deviation just of these numbers, 2.6, using these numbers to estimate the standard deviation of the population they come from gives you a slightly larger number, 2.92. The sample standard deviation is written S. That will always be slightly larger than the population standard deviation. But this one is actually much more commonly used. If we go to the Excel spreadsheet I use to work out the standard deviation of these same numbers, the standard deviation formula here, you notice is STUDEV P. If I just type in standard deviation without the p, because the p is for population, those numbers, that's when I get my 2.91. So these are both the standard deviations. This one's the population, this one's the sample, and in fact this one here is much more commonly used. So if you ever just hear someone saying what's the standard deviation, this is the one they almost always mean, because almost always when you get a few numbers, what you're really interested in is the population, so you work out the sample standard deviation using this. If you have a calculator that gives you standard deviation, this is the one that will probably give you stdev. Sometimes you can force it by doing a special function to give it this one. Now this sample standard deviation is an important ingredient in using our samples to do inferential statistics, to do tests and work out confidence intervals. Because if we imagine a population like this, and often we don't know what the mean is, so the mean income of farmers or mean yield of crops, we don't know what it is. So there's a mystery distribution in the population, some mean that we don't know about, and we're going to take a sample from this population. But the point is, even though we only go and do one sample, so perhaps we could do a sample like this, the first one, this one might be the next one we get, we might get this one next, this one, this one, this one, so maybe a sample of 30 or something. And then we can take the mean of all these and we find that our sample mean comes out here, reasonably close to the population mean. But of course we don't know that it's reasonably close to the population mean. But we want to be able to work out things like, well, let's have a theory about what the population mean could be and work out what's the probability of being, if that's the population mean, what would the probability of our sample mean be? In exactly the same way as we did with the z-scores, except now we're using the mean of this sample we've got in pink here. We want to be able to work out those probabilities. So we need to know something about the distribution of all the possible samples. Are we going to get a sample like this pink one that comes out like that, or what's the chance that we could instead have ended up with maybe this one, then this one, then this one, then this one, this one, this one, this one, this one, this one, and we got our random selection of whatever it was, 100, this one, perhaps one out here, this one, and then one out here. We could have ended up with a sample that gave us a mean. Instead of here, when you calculate the mean of these, we end up with something down here, let's take an extreme case. So, even though we're only usually going to go to the field and take one sample, we want to know about all the possible samples we're going to take and the distribution of those, so we can work out what's the probability that we're going to get one that's close to the unknown population mean or further away than the unknown population mean. So we really want to know the standard deviation of these sample means. The standard deviation of the sample means is what's called the standard error. And as we've seen, for the standard error, if we know the unknown population standard deviation, the bigger and bigger the sample we take, the online demonstration shows, and you can prove mathematically that the standard error, which is the standard deviation of all these possible samples, the spread in the samples gets smaller and smaller by dividing by n. Of course, the problem is we don't know this. So we can replace this by S, which is the spread of our sample, the sample standard deviation. Divide that by the square root of n, and that gives you the standard error. And this then you can use to do your calculations in the same way as for the z-score. Yeah. So you can once you know what a standard error is, you can look at a distance like this from what you think the mean could be up to what you've found. Say how many standard deviations is this? And that will give you quite a low score there. This will give you a higher score, quite a big negative score because you're well below. So you divide this distance by this standard error. Then you can look that up and get a probability. The probability is what you need for your inferential statistics. The final difference is that instead of being called a z-score, it's actually called a t-score now, because this extra uncertainty in having to estimate that means that it no longer follows a normal distribution, it follows a t-distribution, which If you want to look at a picture on the web or somewhere, if that's a normal distribution, t-distribution is pretty much the same thing, but just slightly wider because of the added uncertainty. It's a very rough drawing. So that's why we need to have the standard error, so we can work out probabilities from our samples. I'll next show you one example of how we can use this standard error in a similar way to where we use the z-scores. I've tried to set it out almost exactly the same way. So this should remind you of the first z-score example. The amount of firewood per person used by day, the amount of firewood per household used per day is 82.82 kilograms, and the standard deviation is 0.21 kilograms, same as before. But this time, instead of choosing a single household, we choose 4 households. So what percentage of random samples of 4 households would have mean use less than half a kilogram of firewood per day? Previously asked what percentage of single households. Now what percentage of all random samples of 4 households would average under half a kilogram of firewood per day? Now these things, as before, we're given the mean, it's 0.82, we're given the standard deviation, sample size is 4, and the observation we're given is the threshold value, in other words, 0.5. So what percentage is going to be below that? Now this time, instead of looking at the standard deviation of the individual scores, we've got to look at the standard deviation. How much from sample to sample? How much did the mean of samples of size 4 vary? And it will be less than the standard deviation. And see, this is the formula you should remember from the slide. It's the standard deviation divided by the square roots of the sample size. Let's just blow it up a bit. It's the standard deviation of the population divided by the square root of the sample size. That's the standard deviation of the population, well, divided by the square root of the sample size. Here we know the standard deviation of the sample. So we're actually using that. Because we're just carrying on assuming we know that for a few moments more. Let us back to Excel, please. There. So, having done that, the rest of the z-score is the same formula as usual. It's just the difference between the mean and our observation divided by this standard deviation, the standard error. That gives you a z-score. Looking at the z-score, we find that the proportion of the population of samples, that is, below this would be 0.001%. 0.001, which is, sorry, this is 0.1%. So a tenth of 1% of all samples of 4 households would have a mean use less than half a kilogram of firewood per day. Compare that with the original one. We just took that one household. You've got a 6% chance, 6.4%. So if given that from the same population, you've got a 6.4% chance of picking out a single household which uses less than half a kilogram of firewood per day. But when it comes to picking out 4 households, the chance of picking out 4 households and finding the average of those 4 is less than half a kilogram of firewood per day is less than 0.1%. Dramatically lower. It's because if you get the mean of a sample of 4 varies much less from the mean of the population, because it's unlikely you're going to choose all 4 below the mean. You're going to get some below and some above. Now we can interpret this in the same way as before, using the little twist I said. You can interpret this as a probability. There's a 0.1% probability of choosing those 4 households. So it's very, very unlikely to choose those. Now we can start to apply this to some confidence intervals, which is the first very practical application. Getting more nearer towards stuff you can actually use now. We're going to look at examples of household head age in a rural area. 1972 census in the same area suggests that the mean household head age was 43.5 years. Now, because of reduced budgets, we've only been able to get a sample of 9 households last year. And these are the ages in our random sample of 9 households. And note here, the sample mean is 45 years. Well, what can we say based on this evidence? Well, we won't be so naive as to think that this proves or shows that the age has now increased, because, of course, it could be that when we went there, these 9 people happened to be above average. So this could be sampling error. Perhaps the mean is still 43.5 years. Perhaps it's gone down slightly. Perhaps it's gone up. We don't know. But we can't say that it's going to be exactly 45 because there's bound to be some sampling error here. What can we say? Well, this is where some calculation will come in handy when we get there. Because these are the figures, 42, 45, 38. So this time, instead of a single observation, we've got a set of observations. Problem is, our picture of reality is population has mean, we don't know, standard deviation unknown. We don't know the population, we don't know the standard deviation. So here we can't do any of these calculations. The surprisometer is broken, can't work anything else. We can't even do the backwards calculation because we don't know the standard deviation, which we need to know for that. Of course, as I've tried to point out, the advantage of taking a sample, or another advantage of taking a sample, is that you get a feel for how spread out the population is. You can look at the spread of these numbers here and work out an estimate of how spread out the population is. And we use that to replace the unknown standard deviation. And of course, the thing we use here is the standard deviation, the sample standard deviation of the population, of the sample. So I've typed in STUDEV E7 to M7, which are these values here. I've not put STUDEV P because I want STUDEV, which is the version where it's divided by one less. So it would be, here we have 9 numbers. This would be divided by 8 if you're following those technicalities. Sample size 9. This will be divided by 8. Now this is better because now we've got the standard deviation. We can do all the rest of the calculations. Now all we need to do is assume some picture of the world. We don't need to assume a standard deviation, just need to assume a population mean. So what's the chance that it's still what it used to be, which is 43.5? Now the surprisometer works because it can work out the standard error by dividing the standard deviation by the square root of 9, divided by 3, to get this, and then working out the z value, that it's now called a t value, because we're estimating the standard deviation. But if you follow the technical details, that's great. If you don't follow the technical details, you just need to keep your eye on the surprisometer and the thing that it's showing you, which is this probability value. So that's showing you this is telling us that if the mean still is 43.5, then the chance of selecting 9 people at random and getting a mean from those 9 as far away as we did, from here to here, the chance of that happening is 36%. So 36%, under half, but it's not particularly surprising. So that's not very surprising. Well, let's look at another one. Let's suppose that the mean might have even dropped. Could it have dropped down to 40? But if the mean's actually dropped down to 40, then this is now telling us that the chance of us getting our mean of 45 from our 9 would be incredibly low. So, well 1%, 1.1%, 1.2%, so pretty surprising. So I'd be very dubious about the idea the mean has gone down to 40. We look at what we've got so far. Chance of picking a random sample of 9 and finding a mean age as far away as that, if it stayed at 43.5, is 36%. Suppose the mean age was 40, chance of our sample would then be 1.2%. Now we can keep repeating that process of working out probability from individual values. We get something similar to what we have for the z-scores. We get all the possible states of the world or theories of the world. And for each possible theory about the world, we can work out if this one's true, what's the probability of our observation? And the ones that make it really unlikely, we can maybe say, well, I'm not going to accept that. I don't think that's possible. This one here, 36% chance if that's the state of the world. 53% chance if that's the state of the world. Hard to decide between those two, really. Neither of them make this very surprising. 5.3, a bit unlikely. So, as usually, you've got to put some cut-off point. Say some things are just too unlikely. I think that's too unlikely. That's less than 0.5%, 0.19%. So I don't think it's possible the mean's gone as high as 52. Blast. I don't think this is very likely. If I set a cut-off point of 5%, say, then I can see what range of values here would be within that range of feasibility, so that I have a 5% at least chance of seeing what I've seen. Back in the calculation, let me into the calculation. Blimey. Back in the world of calculation, you can work out the minimum and maximum possible values by playing here, estimating, or directly here by working backwards through the maths. If you want to find out how to do that, you can predict that it's got to be 41.43. That gives you pretty much 0.05, or 5%, and up to 48.56. That gives you the 0.05. So this is the range here, from 41.4 up to 48.5. So we need to decide what level of probability is too low. Usually a standard one. I chose 2.5% at each side, so that really. I chose 5%. Sorry. You only accept states of the world that give my observed results a chance. That give my observed results a chance of more than 5%. So the population mean age could be anywhere in this range, 41.5 up to about 48. That's doing it by trial and error. The exact range we got was that 41.4 to 48.6. So if the population mean actually is outside of there, then the chance of finding an observation as far away as I did is below 5%, so I won't accept it. But anything inside there, the chance of finding a population mean that I did is more than 5%. So I call this a 95% confidence interval, because there's 95% confidence within that range for the mean household age in the population. Note that we don't need to stick with this minimum probability of 0.05. Here I could change it, or I can look at this one where it's set up more neatly. So this is the way you calculate it more positively. You start with the sample values. What range of values of the population mean will keep the probability of this observation above 0.05, and you work through, and it gives you the minimum and maximum. So that's setting out the working backwards in this spreadsheet, but it's all the same maths. But if I said, okay, I'm prepared to go down to a 1%, and that would be a 99% confidence interval, then the range would change to, I didn't change that there, 99% confidence interval, so it goes to 39.8 up to 50.1. So that's the confidence interval I worked out already. That's what I observed, 45. And on the basis of that, and the observed standard deviation in the sample, I was 95% confident that the population mean must now be between 41.4 and 48.6. If I'm happy to go to a 99% one, then it's between 39.8, exaggerate this a bit, not drawn to scale, and 50.2. So a 99% one would be slightly larger. So I'm 95% confident the sample mean is somewhere inside here. Sorry, the population mean is somewhere inside here. And I'm 99% confident the population mean is somewhere inside here. So that the higher level of confidence you want to have, the wider it has to be. And I often use the analogy of, I really shouldn't attempt to draw things like this, but I'll try. If you're trying to catch a beautiful butterfly, you have a butterfly net. If you are 95% confident, you need a net this big. If you want to be 99% confident of catching the butterfly, you need a net that's a bit bigger. So the more confidence you want to have that you catch the butterfly, and the unknown butterfly of course represents the mean, is unknown. If you want to make sure that that's inside the net, you need a bigger net. The higher level of confidence, the greater the wider the confidence interval will be. Of course, if you made a 100% confidence interval, you'd be 100% confident that you caught the real mean inside it, but unfortunately it would have to be infinitely wide, so it would be fairly hopeless in terms of telling you anything. So that's how you create confidence intervals from a sample. And I thoroughly recommend that whenever you collect any data, rather than just presenting means, you give confidence intervals, because it can give the reader a much more clear idea of how accurate your figures are and how much idea your figures give about what's really going on in the population. Closely related to confidence intervals is the idea of hypothesis testing. Whereas instead of specifying a range of acceptable values for the population mean, if you're looking for a mean, we look one by one at particular states of the world, particular theories, and decide whether we're going to accept those or not. For example, we might suggest as our hypothesis that the mean age of household heads is now 43.5. And if we find that this theory of the world makes our observation of 45 too unlikely, too surprising, then we reject this. If it's not too surprising, we stick with this. So if we don't reject the thing we stick with the assumption. That's why it's called the null hypothesis. So if we don't have a finding which is particularly surprising, we stick with our default, our null hypothesis. We have to specify what's going to happen if we do find that this makes our observation unacceptably surprising. In that case, we would reject this, and we'd accept instead that the mean age of the household is now greater than 43.5. So I'm specifying here in advance that I'm only going to reject this if I find a value which is way over 43.5. I'm not going to reject it if I find something which is way under. Because for some reason, maybe I have theoretical reasons or other evidence is telling me that if this has changed, it's only gone up. And that makes a difference to the way we interpret the results. So I can remind ourselves what the value was. That's the 43.5. If I assume that the population mean is 43.5, then the chance of finding something as far away from that as 45 is 36% here. However, I'm not going to take the 36%. I'm going to take the chance of finding something as far above rather than the 36, which is as far away. To illustrate the difference, I have this diagram here. I could decide to reject, this is the theory that this is here, to put some numbers on it, this would be the 43.5. I could decide I'm going to reject if my observation comes out well above this or well below that. And the probability of 36% is the chance of being here or here. That's what the calculation gives me. So there's actually 18 here, 18% chance of being as far above as I am, and 18% chance of being as far below as I am. However, I'm only going to reject if I go above. So I only need this 18 instead of the 18 plus 18. That's because what I'm doing is what's called a one-tailed test, where I'm just testing to see if it's changed in one particular direction, rather than this way where I'm testing to see whether it's changed in either direction. So we can go to a conclusion, which is that the 18% is the likelihood of getting a sample with a mean as large as 45 years, if H0 is true. That's not very unlikely, so this is quite consistent with the null hypothesis, so I can't reject the null hypothesis. To put that into layman's language, there's no strong evidence here that the mean age has increased since 1972. Do another one for comparison. I could have started out with the null hypothesis that the mean age of household heads is now 40, and the alternative is that it's greater than 40. So I put 40 here. I need the one-sided, not the double value, the half value. The probability of it being above that rather than being on either side. So it's 0.0059, which is 0.006. Oh, the actual presentation. 0.006. That's very unlikely. It's below 1%. So if H0 is true, then the mean in the population is still 40. The chance of my finding 9 households with an average age of 45 years is well under 1%, which is incredibly unlikely, so I'd reject it. And the way that these things are reported traditionally is that if you get a value below 1%, you can say, oh, we reject that with 99% confidence. If it's below 95%, you might say, if it's below 5%, you might say you reject with 5% confidence. Because it was common to use these standard levels like 1% or 5%. So I'd say I reject the null hypothesis with 99% confidence in favour of the alternative. And my conclusion in a layperson's language would be there is strong evidence here that the mean age is now above 40 years old, or was above 40 years old in 2011. And that's how you can do hypothesis tests. Now I'll conclude by looking at some further hypothesis tests of the many that are available. They all have different technical details, but they're all interpreted in the same way. And of course, most of the technical working out will be handled by whatever statistical software you happen to use. So the most important point is to know how to interpret the result that comes out, which is almost always in the form of a probability value or a significance value, as it's sometimes called. Normally you begin with null and alternative hypotheses in the same way, and you get this value at the end, which tells you the probability of your results if the null hypothesis is true. If that's too low, then your null hypothesis is making your observations too unlikely, then you have to reject the null hypothesis in favour of the alternative. If it's not too low, you can't reject the null hypothesis. It's consistent with your results. Now, we'll look at the following kinds of tests. To test the difference of two means, so where you have what is called an independent samples t-tests. To test relationships between two nominal variables, so you have categorical variables, such as age, sex, occupation. You want to see if there's any link between those. Or to test whether two variables are correlated, such as environmental degradation and growth. Now, first of all, we'll look at some of these in this spreadsheet. This is what the one we've already done would look like, a single sample t-test. So these perhaps could be ages of the head of households in your survey. We found the sample mean is 45, the sample size 49, and we're testing a hypothesis here that the mean is 40. And in this case, we'd get the chance of being as far from the mean as this is 0.052, so it's slightly greater than 5%. So perhaps we wouldn't reject this at the 5% level, but it's quite low. So this assumption is making the observations here seem fairly unlikely. So the surprisometer is quite high up, so it casts fairly serious doubt on the null hypothesis, but if we work into the traditional confidence levels, we couldn't reject it. Certainly on what's called a two-tailed test, because here my alternative hypothesis here is that the mean is not 40, so I'd reject it if I get well above or well below. So I take the probability of being as far from the mean as the one to work with. So it's a borderline case. Now here are the new ones, and these are actually much more useful, because usually you don't have some hypothesis about what the mean is. You have two samples, so this could be the incomes of two people in two different ethnic groups, or it could be the yield of farms that are using fertiliser and not using fertiliser, and you want to compare whether or not they could be the same or not. So let's say we've got two groups of households sampled from different areas, and my interest is in whether or not the mean age of head of households in these two areas is the same. Not particularly bothered what it is, I just want to test whether it could be the same in each of these two areas. And I'm not going to go through the technical details of the working out, but it's to do with looking at this difference and seeing how big the difference is. Because you'd expect if the mean household head age is the same in each area, then you'd expect that when you select a sample from each area, you get the same answer. But of course, you also get a small amount of variation. The question is that variation small enough just to be random? But this is telling you that if your null hypothesis that the mean age of head of households in the two areas is true, then the chance of taking these two samples of size 9 and 13 and finding a difference as large as you have between them is 0.04. So it's quite unlikely. It's less than 5%. The surprisometer has gone past the 5% level. So that casts serious doubt on the idea, and at the 5% level, or the 95% level of confidence, as we phrase it, I would want to reject the null hypothesis that the mean age of household heads in these two areas is the same. So there's fairly strong evidence here that, in actual fact, there's a difference in the mean head of household age in those two areas. So that's how you can test to see whether two samples have come from areas which have got the same means. The next one is when you have two scale variables. Now here this could be any number of things, ages, weights. I'll show you a realistic example later. This is a more conceptual one. If you have two scale variables and you draw a scatter graph like that, what's the chance that this could have arisen by random happenstance? Yeah. So the correlation coefficient here is 0.81, so 81.45%, 81.45% or 0.81 correlation coefficient, which is a very strong positive correlation. But the chances that you can select this many points and find a correlation as strong as this, if in the population that these points come from, these measurements come from, there is actually in fact no connection between the variables, no correlation. The chance of that happening is given here as 0.0004, so this is 0.4%, 0.04%, so extremely unlikely. It's almost impossible that if there's no correlation in the population, you can find a random selection of points which have a correlation as strong as this. Now let's just generate another set. If you see something like this, well, there's hardly any correlation there visible there, but something like that, slightly weaker correlation, 0.5498 correlation. The chances that this could have arisen purely by chance in the points you've got in your sample is, well, still below 5%. So you reject the null hypothesis that there's no correlation in the population. Just find a better one for you. Like this. This one, for example, kind of there's a suggestion that it looks like a positive correlation of sorts. Coefficient's only 0.462, and when you test that, the chance that this could have arisen by chance, if in fact there's no correlation in the population, the chance of getting a correlation as strong as this is 0.12, 12%, so it's not that unlikely. So in this case, you wouldn't reject the null hypothesis. So the workings out are all different, but the interpretation of this result here is exactly the same as for other tests. If this gets too surprising, you reject the null hypothesis, which in this case is that there's no correlation in the population where these numbers come from. Right. The final kind of test I'll show you is called a chi-squared test, and this is often a very popular one with people that don't consider themselves very quantitative. They do a lot of qualitative work, but they still collect categorical data. For example, here we've got data on men and women and whether or not they're literate. So sort of data that someone might collect quite easily if they're doing village interviews or survey work without doing a great deal of heavy quant studies, just collecting these categories. Yes or no, is the person literate? Are they male or female? And then putting it into a cross-tabulation like this. And the idea is to see well, is there any pattern in this data? Does it seem that there are more males who are not literate than females? Among the females, it's like 50-50 split, literate, non-literate. Among the males, 5 times as many illiterate as literate. Now, the way the chi-squared test works is it says, okay, let's suppose there's no association between sex and literacy, and these are the observed values, and these are what you'd expect if there was no association. So overall, there are 4 times as many illiterate people as literate. So it takes the number of females and males and splits it up in that ratio, and it does the same thing actually in the columns. And then it compares what you'd expect if there was no association with the association here. There's a bit of a complicated formula that measures the difference, but in the end of the day, it all gets calculated according to using a distribution to change it from the measurement of how far this is from the expected values to tell you how surprising the whole thing is. And in this case, instead of using a t or a z, it's using what's called a chi-squared statistic, which is why the test is called a chi-squared test. But if you were doing one of these tests, all you need to know is how to tell the computer how to do it, and then interpret this, which is the same old result on the surprisometer. So because this is only 26%, it's not really that surprising. So it could well be that a null hypothesis of no association in the population between literacy and sex of head of household would be quite consistent with you picking out these 20 households and finding that there's a bit of a pattern here. But that pattern could well have arisen by chance, and the probability of that happening is 26%. So not particularly surprising. You wouldn't reject the null hypothesis, and so there's no evidence here really that there is any association between literacy and sex. Right, now this all looks a bit fiddly doing it in Excel. As I've said before, if you decide when you're doing your own research projects that you'd like to do some quantitative analysis of any sort, highly recommended to get hold, because you're members of UEA, to get hold of SPSS, because it makes doing all these tests far simpler, and really all you have to do then is just interpret the number that comes out the end. For example, here's the age data I've put into SPSS. If I wanted to do one of the tests, say, to see if it's possible that the mean age in the population is, let's do the 43 one. It's as simple as putting that into there, this is the test variable, typing in the value that you're investigating, you say, could it still be 43.5 as it was in 1972, and pressing OK. That's all the work you have to do. Sit back, wait for it to go wrong. It's usually very good. And it gives you all this detail, and it's very boring. So it's like, there are 9 observations, this is the mean, this is the standard deviation. Very boring. But you search for something called the sig, and there it is. There's the 36%, which is the two-tailed significance. Yeah. What you do have to remember is, because we were doing the one-tailed, I don't know if that picture is still there, we're doing the one-tailed, there's 18% on each side, so instead of the 36, we want to halve that. That's one adjustment you have to make when you're dealing with computer software. It usually gives you a two-tailed result, so you just have to know to halve it. So it's 18%, so we don't reject anyway. You can't reject the null hypothesis. But as we found when we said, okay, let's test the idea that, I've gone to a different database. Let's test the idea that the mean is, instead of 43.5, let's test the idea that it's 40. This time the significance comes out as 0.12. If you halve that, 0.06, which is 0.6%, so that's why we did reject it in that case. The idea that it's 40 would make our observations much too unlikely. Right, now a two-tailed one, for this I'm going to use a two samples independent t-test. This time I'm going to use this information on people and views, which I've now put into SPSS. Let's just see if there's any difference in income between men and women. Way to do it is compare, so you just select the test you want, independent samples t-test, and all I'd like to do is to select, see if there's any difference in income. In actual fact, you can do both at once. Test for differences of income and age using sex of head of household. That's the nominal variable. And the values of that are M, F and M. So males. That's it. It doesn't like to hide the results. So it's done two tests at once. What we're looking for is a sig. So comparing income of household, two cell significance is 0.54. You get into technicalities about whether you use this value or this value. Go away. But if we're just testing to see whether they're the same or different, that means that we would have rejected if we found men with lots more than women or men with lots less than women. So you can use the two-tailed one. So we're looking for a difference rather than any specific direction in the difference. So we can use that as it is, so 0.54. So it's very borderline. Probably wouldn't quite reject at 95% confidence, but it certainly casts doubt on the idea they're the same. And similarly for differences in age, quite a similar. So there's some evidence of a difference in age and some evidence of a difference in income, because if we make the assumption that age and income are the same, then we're around about a 5% chance of getting the results that we got, the difference that we got between the two. That's what this test is telling us. But at a 5% level, we can't formally reject it. The next one we're going to look at was a correlation, see if age and income are correlated. Done scatter graphs already, so let's not do that again. We'll just do correlation by variates. both in there. The standard correlation coefficient is Pearson's. This one does do, if you're dealing with some ordinal variables, if both your variables are ordinal or one of them is ordinal, in other words, they're more to do with ranks, you should use Spearman's coefficient instead, because this is not formally valid. But we've got age and income are scale data, so we can use that. And here it flags up. There's the correlation coefficient, 0.037, very, very weak. The chance of getting a coefficient as strong as that, if there's no correlation in the population, is 84%, very, very strong. So it's definitely not significant. So we can't reject the idea that in the population there's no association or no correlation between age and income. I'm going through this quickly because you won't have started to use SPSS, as we don't expect you to be able to do this yet. It's just to show you how quick and easy it is to do these tests in SPSS. The final one is to look at the association between sex and language. It seemed when we did the cross-tabulation in the descriptive part of this session that there was a definite pattern between sex and language. We can recover that by doing descriptive statistics across tabs. I think we had first language of household down the rows, I think, and sex in the columns. Doesn't really matter which row you had it. So that will give you the cross-tabulation. But we can get it to do some extra things. We'd like to have the chi-squared test. See, all the other tests you can use will do various things, but all of them will give you a probability that you have to interpret in the same way. Let's get some details in the cells. That's the percentages in the cells and the expected values in the cells. Okay. So here's the cross-tabulation. It's similar to the one that I showed you before, except it's been expanded because they put the percentage. So this shows you that this is what we observed. 6 females were R-jets, 4 males. So 60% of the R-jets were female and 40% were males. So it gives you the percentages across this way. And it also tells you that if there had been no association between sex and the language of the head of household, you'd expect it to get the values distributed like this. If you had the same totals, the same total number of females, males, same total number of each language group, you'd be expected to see these figures. So you can see how far away you are. You've got more females than you expect in the R-jets here, fewer than you expect here in the Lengits, more males than you expect, and slightly more males than you expect in the Eardens there, fewer females. But is that far enough away to suggest that there's a relationship in the population? Well, the null hypothesis is that in the population there's no association between language and sex, and this is the value it turns out you look at here for the Pearson chi-squared, 0.025. So that's 2.5% chance. So it's pretty unlikely. And at the 95%, because it's less than 5%, you can reject with 95% confidence the null hypothesis that there's no association between first language and sex of head of household, which means there's this evidence is giving us fairly strong basis for saying that there is, in the population, some kind of relationship between the sex of head of household and the first language of the head of household. So that's a roundup of some different hypothesis tests that you can do, and there are many others you can do, but all of them keeps this same principle of assuming something and then assuming a view of the world and seeing how likely or unlikely your observations become if you assume that view of the world. If they become very, very unlikely, very, very surprising, then you reject it. But virtually all tests that I know of, and actually I can't think of any that don't work in that way. So conclusions on quantitative data analysis. We've looked at descriptive statistics and how you can use it to describe and measure the level and spread of the data you have. Then you can go on to look at relationships between different variables and particular techniques you can use for different types of data. And sometimes it's helpful to think of data in terms of nominal, categories, ordinal data, and scale data. Also looked at Z-scores and how Z-scores can help you position particular individuals in particular cases relative to populations. Then we moved on to inferential statistics, how you can try and say something about patterns beyond the data that you've got. And we began by looking at distributions and seeing how you can move from the idea of patterns or distributions to get an idea of proportions, and then the twist is thinking of proportions in terms of probabilities. Because when we move from description to inference, we lose certainty. All you can say is it's likely that such and such is the case, or it's unlikely, but you can never be certain. We looked at sampling and how sampling has some desirable properties, such as making things have a smaller variance. So if you sample, you're more likely to get a sample mean that's quite near to the thing you're trying to estimate. And the central limit theorem, which also suggests that even when you're dealing with distributions which are not normal, as most distributions are not normal, the central limit theorem tells you that when you sample with a big enough sample size, your sampling distribution will be normal. So you can use theories that assume normality. Then we looked at the common logic of all inferential statistics, which is the idea that you have a theory about the world and an observation or observations, and you want to see how surprising does that theory make your observations. If it doesn't make it too surprising, fine, you can stick with the theory. If your theory makes the observations too surprising, then you have to think about rejecting the theory. And that's common to all inferential stats, no matter how complicated they get. Particular techniques we looked at were confidence intervals and hypothesis tests. And the hypothesis tests we considered including t-tests for one sample or two samples, correlation tests, and chi-squared tests. Well, that's all I've got. It's been a long lecture. Thank you very much for your attention. I hope you found some of this helpful. And there aren't any references because this one's been quite a technical lecture rather than looking at literature. But I hope that you feel able to go on and, alongside qualitative approaches, think about integrating some quantitative techniques as you try to understand the problems of international development with which we're all concerned. Thank you very much for listening.